Recording. All right, so far for the previous two lectures, we talked about the enzymatic reactions, focusing on basically the biological meanings, their mechanisms in terms of the biological phenomenon there, where the protein meets the some other protein or the compounds basically, and follow the each steps, how they work in terms of their catalytic reactions. And we took some examples too, like the proteases, the serine proteases, and so on. On the today's lecture, we're gonna delve into the more like a chemical side of the enzymatic reactions. So we're gonna look at the kinetics, as well as the how those kinetics or the reaction rates and stuff like that are involved in the actual biochemical reactions, and how we can describe those reactions in the terms of the biochemistry or chemistry. All right, so you can take this first slide as an outline, basically. So during today's lecture, we're going to talk about these three important quantities. These are really important three quantities that you can actually use them for understanding fully, almost fully, of the enzymatic reactions, the behaviors of enzymes, and so on. So the first one is Km, which is Michaelis constant. And basically, we're gonna, again, talk about this a lot today. But in summary, at the beginning, as a preview, it relates to the how strongly an enzyme binds to its substrates. So it's about the affinity. And higher Km, Michaelis constant, means lower strength of binding. And lower strength of binding between the enzyme and substrate would be the weaker affinity of enzyme for the substrate. And the second important quantity is Kcat, also known as turnover number, and that is basically relates to the how rapid, explains how rapid a catalyst the enzyme is. So it's about the speed or the velocity of the enzymes they have to basically drive any kinds of reactions that it's catalyzing. And it measures the product formation. So that's basically same as the substrate turnover, right? And higher Kcat means, so higher turnover number means a higher speed of catalysis. And the third one is Vmax, and V, we already talked about it. V is for velocity, so that's for the rate of the reaction. And the max is basically the maximum level, the maximum number, or the maximum velocity of that reaction rate. And that relates to the Kcat, which we already talked about here, turnover number, and the total enzyme concentration using this simple equation where Vmax equals Kcat times total enzyme concentration. So again, we're gonna revisit this during this lecture. So don't worry about it if you don't understand what it means. And for Vmax, higher Vmax, again, maximum velocity or the maximum rate of reaction means higher rate of catalysis. And lastly, we use two of those important quantities, Kcat and Km, and the ratio of Kcat and Km would be a measure of catalytic efficiency of an enzyme. Again, we're gonna, talk about this later on, why it means the catalytic efficiency, and also what it actually tells us in terms of the enzymatic reactions. All right, so we're gonna start with the simple enzymatic reaction, where it takes the one substrate, it comes to the transition state basically, where it forms the ES complex. And then eventually it will go to the E plus product, and E will be released, or the product will be released from the enzyme, and enzyme can be recycled for processing another substrate here. And what we're gonna do here is to make a relationship between the rate of the reaction and the substrate concentration using the substrate saturation effect. And hopefully you remember what substrate saturation effect is. That's basically, you look at the different concentration of the substrates and measuring the velocity there, and you can actually see the plateau when the substrate is like a lot there. So a lot of the concentration of the substrate was used. So the velocity reaches to the plateau or the maximum point where it's called Vmax. So, but in the most cases, we're gonna consider the initial state, right? Initial reaction, where the rate of the reaction is basically the product concentration changes over time, so dp dt, and that is same as this K2, the rate constant for the ES2 E plus P, and the substrate basically ES complex, so K2 times ES concentration. Are we on the same page for this, right? Because we talked about this in the last lecture. And when you take into account the total enzyme concentration, that will be any kinds of enzymes that are free, right here on the left side and here on the right side, plus the enzyme that is bound to substrate to form the transition state, ES complex, right? So ET equals E plus ES in terms of their concentrations. And you can basically rearrange this to get the E concentration for this. It's just a simple change, rearranging the like values here. And we talked about the steady state assumption last time, where the ES complex will stay in the similar or the same concentration over time during the reaction occurs, right? So so that means any kinds of ES formation will be the same as ES dissociation back to E plus S, and the dissipation to the E plus P. And you can basically apply the same equation here for the rate of the reaction too, because this is a steady state. So they're going to be always the same amount of ES that is generated and the ES that is dissipated or the dissociated back to the E plus S, right? So here's a relationship there. And again, we're going to ignore the K minus 2, where the E plus P goes back to ES, because this is the initial rate, initial state. So there's not going to be little to no product that goes back to ES complex. Here again, from what is it? The enzyme conservation, equation. The E is the ET minus ES, and we can basically get the rate of the reaction using this similar relationship as you normally would get for the individual reaction steps. So the rate of the reaction for ES formation would be right here, where the E and S are used using the rate constant of K1. So that's going to be K1 times E times S, and both are concentrations. And we can simply replace in this E with ET minus ES here, the relationship above here, to get this equation. And similarly here, the rate of the reaction for the ES disappearance, which is the addition of dissociation and dissipation to the product, would be simply K minus 1 for this ES complex. So K minus 1 times ES concentration and K2 times ES concentration here. Simply, you can put together these rate constants together to get the K minus 1 plus K2 times ES concentration, right? And then basically what we said before in the previous slide was that these both, the rates are the same, right? So we're going to use the same relationship here, where the V for ES formation, which is here, the green equation or the formula here is the same as VES disappearance. Putting it together and then rearrange it to gather all the K's on one side to get this. And here the K minus 1 plus K2 divided by K1 is called Km, or Michaelis constant. That the first important quantities that we talked about at the first slide, in the first slide. And this Km is really important because it can tell the basically the affinity of the enzyme. And we're going to actually see that how it actually tells us the affinity of the enzyme. So Km, again, is the ratio of concentrations of various reacting species. As you can see, ET is used, the ES as well as S concentration too here. And it's going to be expressed in units of molarity because ET minus ES will give you molar as a unit. And S is another molar, right? Molar concentration. So that's going to be molar squared divided by molar concentration will give you just a simple molar. Any questions so far? All right, so now let's rearrange further of this relationship again. This is what we got before right here, right? By rearranging these rate constant values to one side. And that K minus 1 plus K2 divided by K1 is basically the Km, Michaelis constant. So we replace this with this Km, so Km gets in there. And then you can move the ES here, as well as rearrange this other quantities here to get the ES constant here, which is ET as concentration divided by Km plus S concentration. Here, now let's make a relationship between the velocity or the rate of the reaction and the substrate concentration. Again, we go back to the initial definition of the rate of the reaction, which is the dP dt, the product production over time, right? And that's same as K2 ES again. K2 is for the rate constant from ES to E plus P, right? And then that's the ES should be also multiplied there to get the rate of the reaction. And then, so instead of ES here, you put the everything you got so far with the Km value here to get the V equals K2. Again, this is same as here. And then all, everything from here. And here, K2 ET has a special meaning because think about it, K2 is the rate constant from the ES complex to the product and the free enzyme. And here, ET means that the total enzymes. So all the enzymes were used for this K2 reaction, basically. That means it can reach to its maximum kind of capacity for driving to the generation of the products. So this K2 ET will be simply the same as Vmax because again, ET would mean that all the enzyme, total enzymes were used as ES complex in here, right? So you can change this K2 ET concentration to Vmax and keep everything else the same way here. And now you can make a relationship between rate of the reaction V and the concentration of substrate S. And these Kmax and Km are basically constants. Vmax is the maximum velocity or the rate of the reaction, which is constant. It doesn't change, as well as Km value is simply Michaelis constant, right? So that's a constant value that has the each reaction, have its own set value for that. So what does this Michaelis constant really mean? I mean, we could actually drive that. That was really nice. There's a really nice relationship between the rate of the reaction and the Km value there. But what does it really mean? So we can get the two critical meanings for understanding the enzymatic reactions. The first one is that you simply plug the V in here, V, as a half maximum of the rate of the reaction. So half Vmax. If you put it there, that means the max is, Vmax is here. So S over Km plus S should be a half, right? And then since you have S here and S here too, Km should be S. So you have S over 2S to get the 1/2. Does that make sense? So whenever you have the half maximal velocity or the rate of the reaction, you're going to have Km value equals S concentration. And that means you can basically draw the substrate saturation curve here. So here's a substrate concentration. Here's the rate of the reaction that you can measure. Of course, as you increase the substrate concentration, you're going to achieve a higher speed of the reaction. And when it reaches to half maximum of the rate of the reaction, Bmax, then basically what you get as a concentration is the same, of the substrate is same as Km. So you can essentially empirically measure this, Km value there. If you know Vmax value or vice versa too. So that's the first critical meaning, that you can actually get Km value out of Vmax and S concentration, or the Vmax value out of Km and S concentration at the moment. And the second important point is that let's assume that the K2, which is right here to making the product, that rate constant is much smaller than K minus 1, that ES complex goes back to E plus S. And I mean, this sounds familiar because this is one of the critical assumptions, two assumptions of the Michaelis-Menten relationship, right? So if that's the case, then go back to this Km definition, which is K minus 1 plus K2 divided by K1. And you can ignore K2 here, basically, because this is much, much smaller than K minus 1, right? Let's imagine that that's 1/100th of K minus 1. Then it's just adding 1%, right? So you can just ignore that. If that's the case, then Km would be simply K minus 1 over K1. And that's the definition of a substrate constant, which is Ks. And simply, its reaction would be the dissociation of the ES complex, right? So that's E concentration times S concentration divided by ES concentration. And that actually looks familiar because this is a dissociation constant for ES complex. So you can take it as Kd, which is equilibrium dissociation constant for ES complex. So that means when you have K2 much smaller than K1, Km equals Ks, and that equals Kd. Okay? And in here, Km will reflect the binding affinity of ENS because it's all about the dissociation constant. So it's just as simple as this, how much it is dissociated at the equilibrium, right? So if Km is really high, that means you have a lot of free E and S, unprocessed S, relatively small amount of ES complex. So you're going to have a much lower affinity. Would that make sense? Because everything's just, like not combined at all. As opposed to if you have a really low value of Km, that means you're going to have relatively high ES concentration, but really low E and S concentration, where it means that it has a really high affinity between enzyme and substrate. Question? Km and where? Yes, that is correct. So I'm going to go a little quicker, but we'll explain this. I know it can be a little confusing because there are quite a bit of assumptions here. So you have to actually take into account of these assumptions. So the critical assumption here is that if this is not met, then nothing is correct. So only when K2 is much smaller than K minus 1, meaning that this one is much smaller, this one is much larger, that enzymes can actually make the ES complex pretty fairly easily, or the high rate. But once ES is formed, so meaning that enzyme reaches to the transition state, rather than it's moving fastly to the making the product, it actually goes back to E and S free enzyme and substrate form much readily, rather than actually processing further to product, right? That's why K2 is much smaller than K minus 1. And that's the one of assumptions, critical assumptions for Michaelis-Menten equation, or the relationship, basically, right? So we basically use that assumption, and then you look at this Km, which is K minus 1 plus K2 divided by K1. And like I told you, K2 is really small relative to K minus 1. So we can ignore K2 here. And then it just leaves a K minus 1 divided by K1, okay? Which is right here. And that's the definition of Ks, which is a substrate constant. And that is the same as substrate constant is basically how substrate is made, right? From something else. But since we're looking at this reaction, that's going to be the initial product will be ES. Initial reactant will be ES, and the final product will be E plus S. Because we're focusing on this reaction here, right here. So that's a substrate constant. And that is same as dissociation constant, right? Because this is from ES to E and S. So that's dissociation. That's why Km equals Ks equals Kd. Okay? Yes?
Would that be the same as saying Ks for plus final Kd, Kd for plus final Kd?
That is correct. So the question was that whether you can apply the same wording here, statement here for Ks and Kd. That's correct. Only when K2 is much smaller than K minus 1. All right. Oh, one more thing. So I explained that why Km reflects binding affinity, right? And higher Km means lower affinity, which explains here. And lower Km means tighter binding between E and S, or the tighter affinity between E and S. All right, so we talked about the assumption here where we're going to ignore K2 because, just a second, because K2 is much smaller than K minus 1. I'll get there. And the off rate, which is dissociation rate from ES to E plus S will be really low. Let's say that it is really low, as the K minus 1 here is 0.01 inverse second. And let's also assume that the association of ES back to E plus S back to ES complex is really quick, and it's only limited by diffusion. So whenever there's a Brownian motions of enzymes and substrates and things like that, and then when they actually have a collision by chance, by diffusion, they're gonna make the reaction right away. Then that's gonna be only limited by diffusion, right? And that K1, which goes to the ES complex, would be 10 to the 9th of the per molar per second. Then the way you get Km, which is affinity between E and S, would be same as again, Ks, Kd, K minus 1 plus K2 divided by K1. And here K2 is ignored. So you plug the 0.01 to here in the denominator, and the 10 to the 9th to the denominator to get 10 to the negative 11th molar. And that is a really low number, small number. And that means it has a very high binding affinity between enzyme and substrate. Question? Oh, okay. And let's take the another example here, another assumption basically, where the off rate, the dissociation rate is significant, much larger. So here, first assumption was that this off rate is low. Now let's think that this off rate is really high, as K minus 1, 10,000 inverse second. And Km would be 10,000 per second here, which would be put in the denominator, and you use the same diffusion rate, or the ES association rate, K1, as 10 to the 9th here. Then you're getting 10 to the negative 5th molar, which is still looking like fairly small, but it's actually much larger than this 10 to the negative 11th, right? It's a 6 orders of magnitude difference. So that means it's much larger number for Km, and that means it has a weaker affinity, again, between the enzyme and substrate. Question?
So in the first case, if Km is large, Km is small, and there's high binding affinity for the enzyme and substrate, that also translates to there is a slower rate of product formation.
So it is, that's a good question. So question was that now we can talk about the affinity between the enzyme and substrate. Can they actually translate it to the speed or the rate of the reaction too? The answer is no, because it only tells you about the affinity. It's the molecular reactions, right? Molecular interactions between the surfaces, especially on the active side of the enzyme and the substrate. So depending on the design of the active site, it can have a high affinity or low affinity. That doesn't mean that that reaction goes much faster or not. It only tells you that how strongly it binds. For in order for us to tell that the rate of the reaction is accelerated or not, we need to look at the different quantity, which is kcat. So we're going to actually take a look at it a little later. But again, here, everything is on the basis of the assumption where we assume that K2 is much smaller than K minus 1. And again, this is not always true, as we talked, when we discuss what is Michaelis-Menten equation question. I'm sorry, I didn't catch the. Yes, the answer is yes. So again, you can take the Km, same thing as Ks, and also Kd. So the answer is yes, but typically people use Km, which is a constant value, as opposed to Kd. I mean, you can do that, definitely can do that, but Kd can be applied to anything, right? Any kinds of enzymes. So it's more like a broader concept, as opposed to Km is applied only for the Michaelis reactions or equations where enzyme is involved. So when we talk about enzymatic reactions, we typically use Km rather than just saying Ks or Kd.
So are we supposed to just assume K2 always needs to be smaller than K1? Are we ever going to be tested for K2, K1?
So we're not doing that. It's just assumption. So there are a lot of cases where K2 is much faster, much larger than K1 or K minus 1, in which case you can't apply this. It's only for the simple, like elementary, enzymatic kinetics studies at the beginning, where we only had the information and the definition from the Michaelis theory. So we're going to build up on this, and then we'll move to the more advanced level during this lecture. But for now, we're just assuming that everything follows exactly the same way as the assumptions for the Michaelis-Menten equation or the Michaelis-Menten relationships. Okay, so now I talked to you that you can empirically measure the Km value when you know Vmax, and when you can measure the substrate constant. Let's determine the Km value empirically, as well as Vmax here. And these two are fundamental characteristics of enzymes, because that basically tells you how strongly the enzyme binds its substrate, and also how fast it can be achieved, right? At the maximum, with the maximum concentration of substrate. And in order for us to determine this velocity or the rate of the reaction and substrate concentration, we can draw this, again, substrate saturation curve. But it's really hard to do, because you cannot achieve to the really high substrate concentration where you can achieve Vmax. So you can put a lot of substrates there in your reactions, but still there are limitations for the solubility or the number of enzymes that are colliding at a given time, temperatures, and all the conditions where it blocks prevents us from measuring the true Vmax value. So it's really hard. So instead of dealing with this hyperbolic curve, we can actually make it into a much simpler curve or the line for these relationships, where it's using this again, simple line, and it's called Lineweaver-Burke plot or double reciprocal plot. And this is actually a pretty simple transformation where you took the same here, V and Vmax, S and Km relationship here, which is a Michaelis equation. And then you take the reciprocal of both sides. That's why it's called a double reciprocal plot. And again, this was developed by Lineweaver and Burke, so that's why it's called the Lineweaver-Burke plot. And what you do is instead of V, you take the inverse V here, 1 over V. And of course, you have to make an inverse of your left side of the equation too, right? So you change the numerator and denominator here to get this. And of course, you have S concentration here on the denominator, so you can basically rearrange or divide it to the both sides inside the parentheses here to get Km divided by Kmax, Vmax, and there's a inverse S left here plus inverse Vmax. And when you look at this relationship or the equation, it actually resembles a simple line graph here, or the function here, where y equals ax plus b, and where this y is 1 over v, and x is the 1 over s concentration. And here A, the coefficient of the x variable, would be Km divided by Vmax. And B, the y-intercept would be 1 over Vmax, right? So using this information and these new variables and the constants, you can draw this line plot here. And again, the slope here, the slope will be the same as the coefficient of x variable, right? Which is Km divided by Vmax. So here it is. The slope is Km over Vmax. And x-intercept would be located right here. And you can get x-intercept by putting 0 on y here, 1 over v. So if it becomes 0, then you can simply get the 1 over s value here as the minus 1 over Km. And y-intercept is easier, where you can just take this b here, 1 over Vmax right here, right? And again, this is the Lineweaver-Burke plot. And this is really a convenient way to see the relationship between substrate concentration and the velocity. Because this is not hyperbolic, so it's not complicated relationship. It's just a simple correlation between those two variables, right? It's just both inverted. So other than that, you can just simply get the S concentration to get the velocity or the rate of the reaction here. So you can plot it graphically and also empirically measure these values. So imagine that you can just get multiple S concentrations. And if you can measure the rate of the reaction for those concentrations, you can plot the 2 or 3 dots here. And by connecting those dots, you can get all the relationship between the Vmax, Km, as well as S concentration. Make sense? Okay, so how do we actually measure the Km and Vmax in practice or empirically? We measure the initial rates at the different concentration of the S concentration, concentration of the substrate. And you just simply plot it for the 1 over S and 1 over V there. You're going to have a multiple points again, can just connect it to get this relationship for the line function here. But the disadvantage of this is that when you use the certain concentration here, And then you're gonna increase the concentration, right? That means if you take the reciprocal of that concentration, your dot's going to the left side. And because that's gonna be between 0 and 1, you're gonna have a lot of your measurement dots that are clumped together on this region at the beginning of the plot right next to the y-axis. So it can create introduce some experimental errors, as opposed to if you have nicely spaced out dots, then you can draw the line without much less errors. So that's the limitation, but it's still really useful to show that this relationship, and also can get the slope as well as y and x intercepts, where you can get Vmax and Km there. And this is particularly useful for determining how inhibitors work. So you have one simple this relationship here, correlative relationship here, and then as you increase add the inhibitors, you can see that how this is, line changes in terms of its function, the slope or the y or x intercepts and things like that. So you can easily compare them and also measure these Vmax and Km again. All right, so here's a brief summary for you. I'm not going to go over all of them, but we talked about this, enzymatic reactions, lowering the delta G double dagger, and so on. And we are ignoring K minus 2, at least for the when we measure this Km value, right? Certain cases, and this can be ignored when this K minus 2 is less than 10% of S concentration. And again, we talked about this Michaelis-Menten theory, and we used the Briggs-Haldane contributions here, where the ES complex reaches the steady state, and we use this relationship to derive the Michaelis constant and the Michaelis equation too, which is here. V equals Vmax S divided by Km plus S concentration. And there's a definition for Km. And we also talked about the Lineweaver-Burke plot, or the double reciprocal plot, which changed this substrate saturation curve, which is a hyperbolic curve, to the more like a line linear relationship. All right, so far we talked about the first important quantity, which is Km, and also the third one, Vmax. Now we're going to focus on the second important quantity at the first slide, the Kcat value, or turnover number. And that actually goes back to one of the questions about the whether affinity can tells the speed of the reaction. And the answer was no, because Kcat actually tells you the speed of the reaction. So this turnover number is also known as catalytic constant, and that tells you how rapid or how speedy a catalyst in the enzyme is. So it only tells you the speed of the reaction, but it does not tell you anything about enzyme's affinity to the substrate. So its definition is right here using this equation, where Kcat would be the Vmax divided by ET concentration. And it's quite familiar, right? Where you take the maximum rate of the reaction, and that will happen basically when all the enzymes are used as an ES complex. So you take the ET here, and that's going to be Kcat. And that's basically assumption where the Kcat equals K2, because it's all about the making product at the end, right? And that's the slowest step. Again, going back to the first lecture about the enzymes, the slowest step from all the sequential reaction steps will determine the actual overall reaction rate. So K2 is the slowest. So you take K2, and that would be same as Kcat when you use only one kind of substrate. So it makes just one kind of ES, and when all the enzyme is used for making this ES complex. Okay, so in other words, KCAT is the measure of enzyme's maximum capacity, catalytic activity. All right. And there are already Km and Kcat values that are reported, measured and reported for many of the enzymes. And yet you can see their numbers, their values are vastly different from 10 to the negative fifth to the here 10 to the negative 1 or so for Km. Again, the smaller Km, the more affinity you get between enzyme and substrate. And for Kcat, the higher the Kcat value, the more like rapid reaction you can achieve. And you can estimate the efficiency of the enzymes by getting the ratio of Kcat and Km. And think about it, Kcat is the speed of the reaction, how fast that can occur, right? And Km is the affinity. And if you have a higher number, you have lower affinity. So if you take the reciprocal of Km, then it will actually tells you that if it has the reciprocal of Km, you're going to have higher affinity, right? So Kcat divided by Km will tell you how much efficient, how fast that is binding to the enzyme and also driving the reaction in the more faster way. Does it make sense to you? So as you have higher Kcat, you're going to have higher Kcat-Km ratio, and that means you're going to have speedier reaction. If you have higher Km, you're going to have lower Kcat-Km value, and that means you have lower affinity between enzyme and substrate, and that means you have lower efficiency in the reaction, the enzymatic reaction. Question? Higher the Kcat over Km, you get the more efficient enzyme you get. Again, Km works in a reverse way, right? So inverted Km would mean that you're going to have higher affinity. So that's a good thing for an enzyme. And it's the affinity for ES complex, not for the E plus P or E plus S. I mean, it's E plus S. All right, so here, Kcat, again, characterizes how efficiently enzyme works at saturating S concentration. So as you change the S concentration, it'll have higher and higher, it'll reach the higher and high rate of the reaction, right? But you can basically achieve even higher reaction if you have a higher efficiency, which is Kcat value. But in vivo, which is in the cell, you typically have a really low substrate concentration, which is about 1% of Km to the just 1 Km. And think about it, when Km equals S concentration, you reach to the half maximal of Dmax, right, of rate of velocity. So when S concentration equals 1 Km, you're gonna go to the 50% of Dmax, which is not that great. But if S concentration is 0.01 Km, then it's gonna be literally 1% of the Vmax, right? So it's the reaction will be much slower. So that's how what it happens in the cell, in the living organism in vivo system. But we can still derive the meaningful indexes of the enzyme efficiency, which is Kcat, as well as Kcat over Km under these cellular conditions too. So here again, the definition of Kcat is Vmax over total enzyme concentration, right? And we have this Michaelis equation where V is related to the S concentration. And here's a Vmax. So we put the other side of this Kcat definition into this Vmax sorry, we put the Vmax here. So that's going to be Kcat times ET, total T concentration, right? So we put it there. And we assume that this S concentration is really low, like 1% of Km. So let's say that Km is much, much larger than S concentration, in which case you can ignore this S concentration in the denominator, which leaves us to just everything the same, except for that this S concentration at the end is missing, right? And also, when this S concentration is really low, then the most of enzyme will stay in the free enzyme form, right? Unbound to its substrate. So ET would be almost the same as just the E concentration. So here's ET concentration, but you simply change it to E concentration to get this relationship. And again, you can just rearrange this to get the Km over Kcat over Km times E and S concentration. And that looks actually familiar, right? Because it's something, and then E and S concentration would be the velocity or the rate of the reaction. So this would work as a rate constant, right? And that's why this Kcat over Km is important. Again, this shows you how efficient this enzyme is in terms of driving the enzymatic reaction. And that is simply the rate constant. In here, it's going to be the second order because both E and S are used. Does that make sense? The order of the reaction rate can be calculated by the adding all the exponents, right? Here in the velocity equation. But one might think that the why it is actually second order because enzyme shouldn't be involved in the reaction, right? So isn't it E is 0 and S 1 in terms of its exponent to make the first order rate constant? Why is it second? Why is it second order? That's the question. Can be, but I mean, obviously it is called the second order, meaning that this enzyme and substrate, both of them are considered as reactants in here. And they probably have some products. We don't care about the products, right? Or the product concentration. It's all about the rate constant and the initial state, which are the reactants. The reason why is because enzyme here can be also considered as a reactant here to make the ES complex. So think that ES is product and E and S both are the reactants here. So it's a little bit different from what we've been thinking biologically, because enzyme shouldn't involve the Indian biological reaction. But in terms of a chemical terms, you can still add that there. So it is still second order. All right. I know there are a lot of chemical terms and definitions and relationships and things like that, but they're really important for understanding these enzymatic reactions and how they are regulated, and also applied to the understanding the mechanisms and drug design too, where you have to take into consideration of all different components there, including substrates, the enzyme, behaviors and things like that. So these are really important things that you're going to use a lot if you're going to end up working for a drug company, drug development company. Again, Kcat over Km is really important because it describes the efficiency of the enzyme for the processing this substrate to the product when they're not saturating. And it's also called catalytic efficiency or specificity constant. So it actually tells you a specificity too. So imagine that you have speed here and affinity here too. When you have a higher affinity, and also it can be processed in a speedy way, that means you're gonna process specifically binding to that substrate and will process it really quickly. So that sets the specificity of this enzyme. That makes sense? So that's also the efficiency as well as specificity. But the upper possible limit of the Kcat over Km would be the diffusion rate of the substrate, because nothing can be driven even faster than just the diffusion, right? Everything works in there by the molecular collisions, and that is driven by Brownian motions. So unless you somehow accelerate their molecular movements, there's no way to make it faster than just the diffusion. So reaction cannot go faster than diffusion rate here of the substrate. And the only one kind of ES is possible, and the ES complex should be same as total enzyme concentration. That's the two assumptions that have to met to tell that the Kcat equals K2. We already talked about this. In which case Kcat over Km would be simply Kcat replaces with the K2 here. And Km by definition is K1, K2 plus K minus 1 over K1, right? But it's in the denominator, so it flips its order, so it's inversed. And then you change the order of this K1 and K2 to get K1 times K2 divided by K2 plus K minus 1 here. And when you look at this K2 over K2 plus K minus 1, it cannot exceed 1 because these K2 are the same. So you're going to have always a bigger number for denominator unless this K minus 1 is a negative value. And K values, the rate constant cannot be negative, right? It's always a positive value where it drives the reaction there. So that means this value will be always smaller or equals 1 here. And therefore, here, Kcat over Km should be, since this ones cannot exceed 1, should be smaller than K1. Any questions so far here? So here's the relationship, right? And here, K1 characterizes the process of association of E and S to make the ES complex, right? Because I didn't put it up here, but it's right here. So K1 basically, describes the rate of the reaction from the E plus S to ES complex. And again, its maximal rate should be limited by the diffusion. Everything's limited by diffusion, basically. And the diffusion rate, typically, especially in water, is between 10 to the 8th to the 10 to the 9th per molar and per second. And many enzymes already achieve this theoretical limit where the Kcat over Km is around 10 to the 8th and 10 to the 9th. It's by the evolution, we believe. So that means whenever this enzyme meets the substrate, it'll process it immediately, and then we'll just get out of that, make the product, and just pop it out, and then we'll recruit the other enzyme substrate, and we'll process it too. And an example of the such enzyme is beta lactamase, which Kcat over Km, telling the efficiency of the enzyme, is 10 to the 8th per molar per second. So it's close to the this diffusion rate in water. So far we talked about a lot of different quantities and states, the functions and constants and so on. That's just a touch base on the important units for the units for the important constants that we talked about, or the variables that we talked about. So the first one is simply the rate of the reaction, which is V, and that is molar over second, as we know. And the rate constant, the unit of the rate constant changes depending on its order of the reaction. So the first order reaction would be inverse second, and we already actually talked about this in the last lecture. but you can actually revisit that, how it, how you can get this unit. And the second order reaction will have per molar per second. What about the third order? What would you have? So the first one is inverse second. Second one is inverse molar, inverse second. What about third one? Anyone? So for the third one, I didn't put the actual reaction rate equation here, but we'll have another, have the number 2 as an exponent, right? Or the number. So one, let's say that there are 2 reactants. One will have 1 as an exponent, and the other will have number 2 for its exponent. So that's, if you think about that, there are 3 molars there. So that's going to be inverse molar square, inverse second for the third order, and so forth. I mean, keep going, and you just add the inverse molar there for the higher order reactions. And Kd and Km, as we've seen, is having the units of molar, and the Kcat will have the units of inverse second, and that is the same as the first order reaction. And lastly, the Kcat over Km will have inverse molar, inverse second, and that is same as this one, right? Which is a second order reaction units. All right. Any questions so far? So I had to do it pretty quickly because there are a lot of things to cover. But basically, when you take time and slowly just follow the equations line by line, you should be able to understand all of them, what it means. Otherwise, just let me know, as you always do. For the office hour, or you can email me. Now we're gonna shift the gear, and still staying on the same ground where we talk about the enzymatic reactions and its catalytic, its mechanisms, and also with a focus on the kinetics. But now we're going to add one more factor here for the enzymatic reaction, which are the inhibitors. So enzyme inhibitors, or the enzymatic inhibition, is basically the reaction where the inhibitors are involved to interact with enzyme in various ways to alter, especially reduce the activity of the enzyme. And I said various ways, and it can be directly interacting with an active site, or the interacting with the other site other than active site of the enzyme, but still affect the enzymatic reactions within the active site. And these inhibitors are the tools for basically cell biologists and many other biologists, because you can get the quite a lot of information, especially how this enzyme works. So you can better understand the enzymatic reactions and their mechanisms, and also you can use it for the designing the drugs that is effectively working on the certain enzymes that are involved in some kind of disease mechanisms. So pharmaceutical, applications there too. And many drugs are indeed on enzyme inhibitors. So these are the examples. Penicillin inhibits the enzyme cross-linking peptidoglycan strands in bacterial cell walls. We talked about this when we talk about, basically carbohydrates, as well as glycoproteins. And the second example is levastatin, which inhibits the HMG coenzyme A reductase. And this reductase is a key enzyme for cholesterol biosynthesis. And the last example here is ritonavir, which inhibits the HIV protease. So all of them are used as a drug, as you know. And there are different types of enzymatic inhibitions. Largely, there are 2 types: irreversible inhibition and reversible inhibition. And as the name refers, irreversible inhibition will be produce a stable covalent alteration of an enzyme. And that means it cannot go back to the original form of the enzyme. So it's a dead end. And that effect is going to be permanent inactivation of an enzyme. So this is not so much like, desirable for the cellular systems, where it can just trash these enzymes that you produced and then just have to regenerate them, right? As opposed to cellular systems use a lot of this reversible inhibition, which is due to the non-covalent association of the inhibitors to the enzyme or the ES complex or both of them. And there are main subtypes of reversible inhibitions: competitive, uncompetitive, and non-competitive. And they are different in terms of their species that they're binding, whether they're binding to enzyme, ES complex, or both of them. And also, they're different in a way that they're affecting the Km value as well as Vmax values. So we're going to take a look at all these three different main subtypes of reversible inhibitions today. So the first one is competitive inhibition. And it's usually, the competitive inhibitors are usually structurally similar to substrate. So you can actually compete with the substrate to bind to the active side of an enzyme there. And that's why it is called competitive inhibition. And that means it reduces the steady state concentration of ES complex. So normally you would have E plus S that becomes ES complex, and then it will drive to the product and the free enzyme, right? But when you introduce this competitive inhibition inhibitors, then these inhibitors will competitively bind to free enzyme to form the EI complex. So you're going to take up some of these free enzymes. So this ES complex concentration will decrease, right? Ended up having much smaller products. So many of the enzymes were trapped basically in this EI, enzyme inhibitor complex. So that's why it's called, again, competitive. And that can be overcome by adding excess substrates. So think about that. This is all reversible reactions and all about the equilibrium, right? So if you add a lot of substrates here, then you can actually drive this reaction from E plus I to EI to the reverse reaction to get the lots of EI goes back to E plus I. And then since you have a lot of substrate, you can still drive this ES complex formation. So you can, again, get the similar concentration of ES when you add a lot more of substrates. And ultimately, these competitive inhibitors will, even if it is added, you're going to achieve the same Vmax there, but it has to be done with the higher substrate concentration. So how does this inhibitor, especially the competitive inhibitor, affects the kinetics of catalysis? So again, let's look at the relationship between V and S concentration with and without inhibitor. And these are the derivation steps. The first step would be you still use the enzyme conservation equation, where total enzyme concentration is same as free enzyme and ES complex, enzyme in the ES complex. But now, since there's inhibitors that forms the EI complex too, you have to take this into account too to get the total enzyme concentration. And in here, E plus I becomes EI, so the Ki, which is Michaelis constant for inhibitor Ki, would be the basically the same as equilibrium dissociation constant for EI complex, right? We can basically apply the same thing for the inhibitors here. And that's going to be E concentration, I concentration over EI concentration. So rearrange this, to get the EI concentration, you can get this equation from here, and simply put this EI concentration back to this enzyme conservation equation to get here EI is substituted with this EI over Ki to get this relationship where total enzyme concentration is quite similar, E concentration and ES concentration, which is the same as the enzyme conservation equation without inhibitor. But instead of just leaving these two, you add this one more factor that is multiplied by the E concentration here, which is 1 plus I concentration over Ki. Again, Ki is the Michaelis constant for inhibitor. Again, the next step would be getting the rate of the reaction relationship where K1 E and S concentration, which is the formation of ES complex, is the same as disappearance of ES complex, which is K2 and K minus 1 and ES complex. Again, we talked about this a few minutes ago. And you basically rearrange this to get the Km value here. Move this ES to the left side and the K1 to the right side. And you get this right here. And you replace this to the Km here and rearrange again to get the only E concentration, to get the E equals ES concentration times Km divided by S concentration. And we got the this ET concentration from the enzyme conservation equation and plug this ET value, plug this E concentration value to the this equation to get here. So ET, instead of E concentration, you put this ES Km divided by S here. And then again, here's the same ES here. So you put it together to get this relationship here. And then, change this equation in a way that you can get ES concentration. So put this on the left side and then move everything to the other side to get this. And then, again, the definition of the rate of the reaction is K2, ES concentration. So you put this value, so K, here's a V, K2, ES concentration. You put this ES equation into this definition of the rate of the reaction to get this one. I'm not just reading it because it's too long, but and then this K2 ET concentration is the same thing as Vmax. And we talked about this multiple times actually, where all the enzymes are used as a ES complex for the K2 reaction, which goes to the ES to E plus P. So that becomes to Vmax. And you have everything else there the same way. And this one is looking similar to the original Michaelis-Menten equation, where V equals Vmax S divided by Km plus S concentration. But only the difference, again, take a look at it. This one is the final one, which is the same as this one here. And the only difference is that you have this 1 plus I concentration over Ki that is multiplied by this Km right here, right? So that means this Km, Michaelis constant, was increased by the factor of this 1 plus I concentration over Ki. And you can take this as alpha here, 1 plus I concentration over Ki. And think about it, when this alpha is 1, that means Km will be the same thing, right? So, and when it's 1, that means this I concentration is 0, right? If this one becomes 0, then alpha is going to be 1. And that means whole thing is 1, so Km stays the same way. And that's going to be where there's no inhibitor. Because again, this is the I concentration is 0 when alpha is 1. So that's the saturation, the substrate saturation curve that you would normally get. But as you increase the concentration of inhibitor here, imagine that, this one goes up, then alpha increases, right, above 1, and that means your Km value increases. As your Km value increases, denominator increases of this rate of the reaction. That means the rate of the reaction decreases overall. So you're going to end up having a more like a flatter curve here. And as you increase the concentration of this I, then you're going to have more like a flattened curve here. But in the end, imagine that, as you increase the substrate concentration, at some point you're going to reach to the Vmax and the higher velocity here. Does it make sense? So when you focus on the same substrate concentration point, where let's look at it here, Km, without the inhibitor, you're reaching exactly the half maximal of the rate of constant, rate of the reaction, which is Vmax, half Vmax, right here. But if you add more and more of the inhibitor, the rate goes down, rate of the reaction goes down. So you're going to have slower and slower reaction. That means the lower and lower value for your initial rate of the reaction. Question?
Yeah, I was just going to ask if it was possible for any of those lines to intersect once the substrate concentration are really running around, or will they have
So is that going to breach, you mean?
like is the green blue purple line, will they ever cross over one another?
You could. So the question was that I already kind of talked about this, but in the kind of confusing way. But as you increase a lot of this concentration of substrate, even if in the presence of inhibitors, you can reach the point where these curves are going to. So even if your velocity or the rate of the reaction goes down, if you increase it a lot in here, right, between 3 and 4 km of the substrate concentration, you can reach the half maximal of the rate of the reaction for sure, right? So it's only the matter of adding more substrates to get to that reaction. So that's kind of nice segue because it will not change the Vmax at all. So you can still reach to Vmax even with the presence of the inhibitor, but it'll only alters the Km value because Km now becomes the Km with this alpha value, which is 1 plus I concentration over Ki. And this is basically the same thing here. And the most important thing here is that you can again reach the Vmax with a much higher concentration, but the Vmax will not change. And since, again, looking at it in a hyperbolic curve is kind of a little difficult, especially to compare those curves between the different inhibitor concentrations, we can convert it to the Lineweaver-Burke plots, where we can see the relationship in the linear way here. And adding the competitive inhibitor, again, will, when you look at this curve, will change the slope, but will not change the y-intercept. So y-intercept is 1 over Vmax, right? And I told you that adding the competitive inhibitor will not change Vmax. So the y-intercept will stay the same. But the curve, the slope changes because the slope is Km over Vmax, and Km changes. Especially Km gets bigger because alpha, okay. Because alpha can only be 1 or higher than 1, right? So Km increases, meaning that you're going to have steeper slope here. And since your slope changes, you're going to see that the x-intercept changes too, which is -1 over Km. So Km value, of course, changes, and Km increases. So you're going to have a larger um, x-intercept here. Okay, so the second one is uncompetitive inhibition, and that means the inhibitors binding only to the ES complex, not the enzyme or the active site. And so that's why it is called uncompetitive. It's not going to compete with the substrate directly. It only affects the stability of this ES complex by changing its its conformation or the affinity to the substrate. So instead of having EI complex for the competitive inhibition, it will have ESI complex here, where inhibitor binds to the ES complex. And in here, it uses K prime I as its Michaelis constant. And you can go through the same derivation for the rate of the reaction equation here. But what you're going to get in the end would be looking pretty much the same. And I only highlighted the changes in red here from the original Michaelis-Menten equation. So you're going to have this Vmax, instead of the Vmax, they're going to be Vmax divided by this alpha value, which is 1 plus over I concentration over Ki. And the Km will be also affected here too with the same factor. And that means when you look at it in the Lineweaver-Burke plots, since both Km and Vmax will be affected with the same factor, it'll keep the same slope. So when you have inhibitor, it'll keep the same slope, but the y-intercept, which is 1 over Vmax, will increase. Because again, this alpha value is always larger than 1 if you add inhibitor. And the since this this factor is divided by this Km as well as Vmax, you're going to have higher apparent Vmax values, as well as higher Km values. So your x-intercept also increases too. And you can basically, as you increase the concentration of inhibitors, you can get a lot of different slopes, parallel slope lines here that is increasing its y-intercept. Okay, and the last one is the non-competitive inhibition, which is also called as mixed inhibition, and that inhibitor binds both enzyme, free enzyme, as well as ES complex too. And that means that it will not bind to active site, because if it binds to active sites, it will exclusively work on these free enzymes, right? But it also works on the ES complex too. So it's going to be working in the binding to the other place, but affecting enzyme, free enzyme, binding to substrate, as well as the stability of the ES complex. And if you derive the function, the rate of the reaction in the similar way as we did for the first one, competitive inhibition, you're going to ended up getting this equation for the rate of the reaction, where the only Vmax is affected by the alpha factor. Again, the same thing, 1 plus I concentration over Ki. And this is only when Ki here is the same as K prime I here. Both are can be different, right? But we're just assuming that these are the same to make this equation much simpler. And here, as you can see, Km is not affected by this inhibitor, but only Vmax is affected, especially decreased by the factor of this alpha. And again, when you look at it on the Lineweaver-Burke plots, basically, here's the slope, and of course, it only affected the Vmax. So it's gonna change this y-intercept, but x-intercept, which is minus 1 over Km, will not be affected. Again, Km stays the same here when Ki equals K prime I. But when these two values are different, two Michaelis constants are different, then now this will affect the both Km and Kmax. Ended up having still looking like the fanning out the multiple lines out of the same one dot. But this dot, instead of becoming the x-intercept, it'll be something a little above the x-axis. So this relationship is really important. This is a summary of the all different kinds of inhibitions here. When there's nothing there, here's a simple original Michaelis equation here. When there's a competitive, only Km is affected by alpha, and alpha is 1 plus I concentration over Ki. And for uncompetitive ones, both Bmax and Km is affected. And for the mixed one or non-competitive one, this only Vmax is affected when alpha equals alpha prime, or the Ki equals K prime I. But if they're the same, then it's going to be only Vmax that is affected. And I'll spend another like 1 minute to explain this slide. So far we talked about all the unimolecular reaction, basically just talking about one substrate for the enzymatic reaction. But typically, there are at least 2 enzymes that are involved for enzymatic reactions in the cellular systems, and they are called bimolecular reactions or multimolecular reactions. And these are the examples of transferases, oxidoreductases, and things like that, where one functional groups move from one substrate to the other substrate. So you require at least 2 substrates here too, right? And this works in the 2 distinct the mechanisms. First one's sequential reaction, and the other one is the ping pong reaction. Sequential reactions is called a single displacement, and ping pong reaction is called double displacement. And sequential reaction is subdivided to ordered and this random sequential. And for the ordered one, basically, here's an enzyme. For the we're talking about the bimolecular reaction where A plus B becomes P plus Q by the help of enzyme E. And here, the ordered sequential reaction will have the enzyme first, preformed, and then we'll bind A first, and then have to bind B next to become this EAB complex that becomes to EPQ, the products, and then P will be released first, and then Q will be eventually released to get the free form of the enzyme. But the random ones basically can introduce either A or B without caring too much about the order of these 2 substrates, but will eventually make this EAB complex to make the PQ products, and then PQ products release will also be taken place at random order. And lastly, the ping pong reaction would be the one substrate comes in, make the EA complex, and then make a P product, and then it will be released. After that, this enzyme becomes a different conformation. In the different conformation, make the F sort of shape. And then this F will bind to the B specifically, again, next time, to get the FB complex to make the Q product, and it will be released to recover the original form of the enzyme. So that's it. And again, there are lots of information here, but take your time and just you can always come to the office hour when you have a question. Did I actually?